to thank you all for coming, especially my family for being here. This is just wonderful to have you all here and to have all your support and to have worked with many this project. So my name is Mary. I'll be presenting my master's thesis today. Woo! Yeah. So I started working with Steve Marshak and Joe DeVera on this project, and I'll get to it in a second. But before I start, I want to apologize for using feet today instead of meters, because our topographic maps are in feet, our drill holes are in feet, and it's just the way we work. So let's get started. How did I become interested in studying faults in southern Illinois? Well, I did some mapping for the Geological Survey with Joe and John. We found a complexly faulted area, to put it simply, and at the scale we were mapping, we couldn't examine the faults in detail, so I decided to take this on as my thesis project. So I'll be telling you about the Wolf Creek Fault Zone, which is part of the St. Genevieve Fault Zone in southern Illinois. So a little bit about what I'm going to cover today. I'm going to start with an introduction, background, and motivation for the study. I'm going to go over a little bit of history of study in the area, my methodology, stratigraphy of my study area, some of the structures like folds and faults that I see in the area, the geologic map that I made of this area, cross sections that illustrate a slice through that geologic map, and I'm going to propose a tectonic model for the mapped area, and then I'll discuss a little bit about the global tectonics at the Mississippian-Pennsylvanian time boundary, and I'll finish with my conclusions. So I'll start out with my introduction and motivation for study. So let's get situated in southern Illinois here. We have Missouri on the left and Illinois on the right. The Mississippi River flows through the region, and this is a satellite image, so the darker green areas show forested areas like the Shawnee National Forest and the Ozark Mountains there. And some features of interest in this region are the Ozark, the rhyolites of the Ozark Dome in Missouri, some nice scenic vistas, wineries for the California folks, and some nice bike riding and outdoor activities in southern Illinois that I enjoy as well as many others. So if we strip away the land cover from that satellite map, and we look at the terrain map, this is from Google Maps, we can see features like the floodplain of the Illinois River, which is the floodplain of the Mississippi River, which is relatively flat. And we see, in stark contrast to that, the topographic highs trending in this sort of orientation. And I want you to notice this sort of northwest trend of the topographic highs, along with the bend in the Mississippi River here. And the trajectory of the Mississippi River here is controlled by faulting. So, now to the meat of what I'll be talking about today. The St. Genevieve Fault Zone is our main fault of interest. It's a zone of uplift, and the Pomona Fault to the north is thought to be a splay off of the St. Genevieve Fault. Both the St. Genevieve and the Pomona Fault were active during the late Mississippian and early Pennsylvanian time. So here you see the faults manifest in the landscape, and the high areas have been uplifted by faulting. And they're more resistant to erosion. So my thesis study area is the Wolf Creek Fault Zone here in red. And I want you to notice a few things here, because I'm going to get back to them later. Number one, the St. Genevieve Fault Zone dies out to the southeast, just near my study area. And number two, I want you to notice the complexities and the subsidiary faults of the St. Genevieve Fault Zone. We call these subsidiary faults, like these ones and these ones, we call those fault splays. So I want you to keep these things in mind, because we're going to get back to this point about the spatial relationship of the Wolf Creek Fault Zone to the tip of the St. Genevieve Fault Zone at the end of the talk. But let's zoom out a little bit from here, and we can place the Wolf Creek Fault Zone, which is shaded in yellow here, in a more regional context. We can see that the St. Genevieve Fault Zone that I showed in the previous slide continues for quite a distance into Missouri. We can see the Cottage Grove Fault system which is another large northwest trending fault system in the area. And we see some sort of north to north-northeast trending structures like the Degonia monocline and the Bodenschatz lip fault. So I want to mention here that the Cottage Grove fault system and the St. Genevieve both have documented strike-slip movement on them. And while I'm here, I should also mention briefly the nature of mid-continent faults is such that it's believed to be a fault in the basement at depth that when reactivated throughout geologic time, the sedimentary strata above gets folded and warped. But geologically speaking, we're going to be talking about the region including the Illinois Basin and the Ozark Dome. And I'll explain this in cross-section here. It's a little bit easier to see. Say we take a slice like this through that area and we look in at it, we're going to see here that a basin is a continental scale depression in which sedimentary strata are preserved, and that the dome is where the igneous basement rocks are uplifted and the sedimentary strata are eroded off the top of them. So these broad basins and domes, in many places, are separated by large fault zones that either cause or accommodate the relative uplift of the domes and the relative subsidence of the basins. So we can see this relative uplift in a 3D picture of the top of the Precambrian basement, and I'm not sure if you can see here, but the lighter areas are topographic highs where the elevation is high. The Ozarks are above land surface, and then the deep red color is where is actually several thousand feet below the ground surface. So this is the 4-state region including Missouri, Illinois, Indiana, and Kentucky looked at from an oblique view. And the elevation change between the Ozarks and the Illinois Basin along this transect, which is the St. Genevieve fault zone, is roughly 3,000 feet in that location. But there's a much greater relief from the Ozark Dome to the deepest part of the Illinois Basin, which is in western Kentucky. So let's zoom out. Well, we'll keep sort of that same view, but we're looking at plan view now. And we can see that the entire mid-continent is riddled with faults. Notice some other northwest trending structures like the Cottage Grove, which is a little more west-northwest trending. But then in northern Illinois, the Sandwich Fault Zone, which I've done a little work on. So, just to make this very clear, what is my motivation for this study? I wanted to map the area in detail, so this became my thesis project for the past 2 years. And you might ask what fueled me. Well, I began thinking about the nature of the faults within the Wolf Creek Fault Zone by drawing sketches like this, and this, and this. Brett and Joe are very familiar with those ones. And I wanted to know what was the nature of these faults. I wanted to know how did they form. I wanted to know what the relationship was to the St. Genevieve Fault Zone, and what did these faults look like at depth. And so nobody had yet synthesized a model that related the faults in a regional tectonic setting. And nobody had yet come up with a watertight argument for how the geometry of these faults are related to the St. Genevieve Fault Zone. So, in essence, we did some more mapping, and at some point, a pattern appeared. And so, the goal of my thesis study was to synthesize a model for fault development within the Wolf Creek Fault Zone. Okay, so next, to the history of study in the area. Studies began in the mid-1800s with Amos Worthen. This is an etching of Grand Tower, the outcrop of Grand Tower, which is right near my study area. And the landscape is a little bit different than it is now. Studies like that led to people looking for oil in southern Illinois. Stuart St. Clair did some work in the middle of the 1910s, 1920s, made maps that looked a little bit like this, showing the structure in general, made a very good attempt at stratigraphic correlation, and many of those things are similar now. And they drafted cross-sections of these areas. So they had a pretty good idea of what was going on here. Geologic mapping efforts after oil exploration studies began with George Ekblaw, and you can see one of his original field sketches here. Can we flip the lights real quick? So correlating outcrops from area to area and making a diagram that geologists are familiar with, correlating with stratigraphy in the area. Just keep the lights up there for just a minute. So he continued with, field notes, detailed sketches of relationships in the field. And later in the 1960s, some SIU students did master's theses where they mapped this area. And then we continued on with recent mapping in the 1990s by Joe, Brett, and John. And again, as you see, the field notes don't change that much through time. We have some detailed field sketches and some detailed notes and a little bit of humor. Like, I am accompanied by a dog who likes to paw over me and my notebook after taking dips in the stream.
John.
So my notes look much the same, but with a little less humor than John's. But still, detailed field sketches and stratigraphic correlations, and just notes about the rock types and the landscapes I see there. So these are actually some of my field notes from this particular study in Southern Illinois. So I joined this mapping team with Joe and Brett and John in 2007, covering parts of Southern Illinois, Western Illinois, Northern Illinois, and I'm currently back in Southern Illinois temporarily. So now to my methodology. So part one of my methodology was fieldwork. So here are some of my field tools, my field notebook, some acid, hand lens, geologic hammer, my Brenton compass. I used GPS for this study, and a camera to take photos of outcrops like this and fossils for being able to understand the rock units. And just to talk a little bit more about the fieldwork conditions, we typically do the fieldwork in the winter because in summer brings heavy vegetation and ticks. Other dangers aside from ticks are bluffs, steep bluffs and deep sinkholes. And I found in this area that, well, this is sort of the nature of outcrop here. Sort of scattered outcrops, and sometimes few and sometimes relatively more. This is called a pretty good outcrop. If I saw that, I would get really excited. So I found the landowners in this area of Southern Illinois to be generally helpful. Some of them had signs posted like this one. And I continued, I kept walking. And then, so that was part one of my methodology. Part two of my methodology was drilling. So we drilled for rock core, like here. So I would decide to drill in an area that would answer scientific questions for us. And in this case, for the study, it was faulting. We wanted to understand how the faults were working and the distribution of them. So we see faulted rocks in one of the cores we drilled on the Pomona Fault here. You can see the tilted bedding there. And after we drill the hole, I make detailed notes about what we see inch by inch, and then I also use descriptions of water wells from other geologists to augment what I see. And step three of my methodology was the computer data analysis, which should not be minimized because it was a significant part of, especially the last part of getting all this work to come out and be able to present it to you in this format. So I used ArcGIS to organize my field data. So ArcGIS is a geographic information system which is useful for data that needs to be geographically referenced, like field notes and drill holes, like point data or line data. And just to say, the GIS is a steep learning curve, but once I figured it out, it allowed me to look at hundreds of data points pretty easily and to add or delete points with the help of Jane. And also with her help, I was able to design a tabular data format to look at the structural data like strike and dips for bedding attitudes. And then I used this later to code these field notes with different colors to show the distribution of the rock types. Okay, so now I'll describe the stratigraphy of the study area. So the first step in a mapping project is to understand the character and the thicknesses of the rock units, and that's what this diagram here on the right aims to show. But on the left is a generalized stratigraphic column of the rocks in southern Illinois. The sedimentary succession here above the Precambrian basement is about 14,000 feet thick. And this image is to scale, so you get a sense of the thicknesses of the Cambrian and Ordovician and so on and so forth systems within the Paleozoic. And what we can see from this is that we can see the relative thinness of the strata that are exposed within the Wolf Creek Fault Zone. So let's move over to the right. We'll enlarge that, the stratigraphy there, and show some details. So now this one at the right is at an expanded scale. And we can see here that the strata that are exposed are of Upper Mississippian age and lowermost Pennsylvanian in age. So they include the Mississippian age Menard limestone, the Palestine Formation, the Chlor Formation, the Degonia Formation, the Kinkaid Formation. And then the Pennsylvanian sediments on top of that belong to the Caseyville Formation. The Mississippian units are a succession of limestones, shales, and sandstones that reflect deposition in a shallow continental sea that underwent frequent fluctuations in sea level. And after the deposition of these Mississippian rocks, there was a long period of erosion. And then, on top of that unconformable surface, the Pennsylvanian Caseyville Formation was deposited, and due to the prior erosion that occurred on the surface, the Caseyville rests in the upper Degonia in places. And sometimes the Kinkaid Formation was completely removed. Okay. So now I want to emphasize my point about the significant period of erosion that occurred after the end of the Mississippian time period. So this gap of time in the rock record is called an unconformity. And this particular one is called the subabsoric unconformity, and it's a major sequence boundary that is recognized by stratigraphers. So just to describe this a little bit, a period of widespread erosion throughout the entire Illinois basin weathered away the upper Mississippian strata, leaving a deeply scoured surface, as shown here. The deepest scouring occurred along the flanks of the Illinois basin, as shown by the oldest units in red and gray. And the youngest sediments were preserved near in the center of the basin, as shown here by the units in blue and sort of pinkish. So, the Pennsylvania rivers carried sediments from the Appalachians, which were to the northeast, through channels that flowed to the southwest. And we can see, we have evidence of this from a paleocurrent study by George Desborough in 1961, where he found that the paleocurrents in the Pennsylvania sediments were diverted to the southeast along this zone of uplift, which is the St. Genevieve Fault Zone. So that was one piece of evidence that showed that the St. Genevieve Fault Zone was a topographic high in Mississippian time. And then another study by Richard Poore, actually many years before that, in 1925, showed that Devonian age cherts, which are exposed here, were incorporated into the basal Pennsylvanian conglomerates in this region, which is near my study area. And there's my study area in red. So my main point here is that the unconformity between the Mississippian and Pennsylvanian rocks occurs across the entire Illinois basin. So there were challenges in mapping these rocks, and I quote Amos Worthen from 1861, "From their general similarity in lithological character and the wide range of the characteristic fossils of the group through the whole series, it is difficult to decide what part of the series an outcrop of limestone belongs, unless the associated beds are also well exposed, so that its position can be determined by the sequence of the strata. In sum, the rocks look very similar in this area." In addition, we have isolated outcrops and faults cutting these rocks to add to the difficulty. We have an outcrop here of, can you flip the lights for a second? We have an outcrop here of Caseyville sandstone and the Degonia sandstone, both forming sort of massive bluffs with this 5-foot staff for scale. And each silicioclastic unit in this part of the sedimentary succession contains a fine-grained quartz arenite. And then there is the nondescript brownish-gray limestone, which occurs in most of the limestone units, although there are some grainstone beds and locally oolitic beds that could be traced in the Clore and the Menard Formation. But despite these problems, there were a few key characteristics that aided me in mapping these rocks. And I won't describe all the units now, but I'll just describe a few that were well exposed. So there's a limestone and shale unit called the Clore Formation. I was able to find what I call a brachiopod graveyard stone, which is actually a pack stone, but with many brachiopods. And John Nelson was able to find a diagnostic yellow bed at the top of the Clore that he found as a mappable unit. But when I was out there, I found that limestones from other formations could weather to form this yellowish rind also. So next, on top of the Clore Formation is the Degonia. And the Degonia is a sandstone unit with a massive sandstone at the base, siltstones and shales near the upper part. And it tends to be thinner bedded than the Caseyville, as you can see from this outcrop here. It has abundant sedimentary structures like ripple marks. And during the course of the study, we found a brachiopod sandstone, which is new in the upper part of the Degonia. Above the Degonia Formation is the Kinkaid Formation. The Kinkaid is a limestone unit with some shales. The dark gray chert nodules, as shown here, are common in the lower part, along with abundant bellerophonic gastropods in the lower part of the Kinkaid as well. After that time of erosion, we get the Caseyville Formation deposited at the top with its chert clasps within a coarser grained sandstone. And the Caseyville is a massive sandstone unit. It has high angle crossbeds, which you might be able to see there. And it sort of has a massive character and outcrop. Okay, so I'll show you a few more field photos showing the structure that I observed in the area. Here are some beds of the Degonia sandstone in a creek, dipping about 20 degrees. Here we see the same Degonia Formation forming a bluff that is tilted and it's diving into the stream. And as we say as geologists, it's V-ing downstream. I also see normal faults. Here's a small-scale negative flower structure in the Degonia Formation as well. And we see faulting in the Palestine Formation with about a foot, 1 inch of normal sense displacement. You can actually see some of the fault surface there. Another thing I observed associated with this faulting that was typical is float blocks, so blocks that have fallen off the main bluff and they're now in the creek somewhere, but nearby the fault, this alligator texture. And here I was actually able to find a fault surface, which when zooming into that area, we actually see slick insides, faint slick insides in the trend of my pencil there. So I put all these observations together to make the geologic map. And next I will show you that. So to make the geologic map, I trace the map units across the landscape. So here you see the distribution of rock formations, which are indicated by the different colored polygons here. The faults are indicated by the black lines, and the larger bounding faults are indicated by the heavier black lines. And the detailed mapping that I did for this area, for this study, is outlined in red, and the drill holes which helped me constrain my data are in orange. So it gives you a sense for sort of the data, the distribution of data. And I filled in some of the areas that I couldn't visit with field notes from other mappers like John and Joe especially. So to make this map, I began with a compilation of 4 different quadrangle maps with different color schemes. I took those original 1 to 24,000 scale maps and replaced those with a new map of this Wolf Creek Fault Zone area at the 1 to 12,000 scale, so blown up about 2 times. And some changes to the new map are that I was able to extend these faults here further to the south. I was able to, I think, improve the accuracy of mapped faults and to show the rock formations with consistent colors across the entire mapping area. And so from the detailed mapping, I was able to identify 3 structural domains, which are outlined in blue here. I was able to identify a central domain where the rocks are flat-lying and undeformed, and the western domain where we have rocks dipping to the west and to the east, and then similar with faults trending north-northwest, and then the eastern domain where the faults trend north to northeast, also with a west dipping domain and an east dipping domain. The red line here indicates the axis of dip reversal, which can be thought of as an anticline, but it's a little bit different because we see several normal faults cutting these rocks here, causing repeats in the stratigraphic section. So I'm cautious to use the term anticline because it's not an anticline in your typical sense. So that's why I call it the axis of dip reversal. So the repeats in section that I see throughout this area are typically preserved in the Degonia Formation, which is I showed you many photos of the Degonia Formation. That was the most well-exposed and traceable unit in this area. The beds dip about 16 to 20 degrees on average within the western domain and the eastern domain, both on the west dipping and east dipping limbs of each of those. And although the average is about 16 to 20, the dips range from typically like 5 to 50, and in places even steeper than 50 degrees. So overlaid on the results of my mapping and identifying these structural domains, I overlay lines of cross-section which are A to A prime and B to B prime, which I will show in a minute. But first, I'd like to use cross-sections to explain our initial hypotheses based on mapping done 12 years ago and how my cross-section tested this hypothesis. So let me describe this previous hypothesis. John and Joe, who mapped the area in the 90s, thought that the faults were caused by gravity slumping into a Pennsylvania river channel. They envisioned a scenario where, in the upper image, upper Mississippian units, after they were deposited, were eroded down to the Menard Formation. And this created accommodation space for the faults that would then form. They envisioned that these faults formed by seismicity along the St. Genevieve Fault Zone, shaking the area, triggering slumping into the Paleo Valley, and the sliding surface for these blocks was provided by the upper shaly part of the Menard Formation. After that faulting, the Pennsylvanian sediments came in, sealed the faults, and then subsequent erosion since that time gave us a window into the system of paleoslumps. So I tested this idea by sketching a cross-section. We'll start out by looking at the cross-section A to A prime, which is from southwest to northeast. And this cross-section actually shows a transect just as if you were walking down Wolf Creek. And this cross-section and these exposures in Wolf Creek are the ones for which this study area is named. So this section is to scale. So the horizontal scale equals the vertical scale. So there's no vertical exaggeration. I constructed the cross-section to scale so that the unit thicknesses, the fault dips, and the bedding attitudes were true. And so what I want you to notice here is that the rock formations are tilted by a series of normal faults, and that the beds all dip mostly to the northeast. The Degonia, which is the green unit, is the marker horizon that formed the most persistent ridge in this area. And we ended up calling them hogbacks or ribs when we were out there. My data points are the small yellow circles with a little dash on them indicating the bedding orientations that I measured in the field. And the thicknesses of the units, like here, are constrained by drill holes in the area. One of the drill holes that we did, this GG number 1, penetrated a fault, and we saw thinning of the core formation, which was an indication that we had a normal fault cutting through that drill hole. And so that confirmed the presence of the faulted strata in this area. Next to that, we see a small fault that underwent normal sense displacement in the Mississippian. Then the Pennsylvanian sediments were draped over top of that, and it was later reactivated probably in the early Pennsylvanian. And so it's possible that many of these faults could have been reactivated during the early Pennsylvanian, during this time of faulting that occurred then. So now, looking back at that gravity slumping hypothesis, because I constructed this cross-section to test that idea, we see that there are a few problems with this hypothesis. When we plot the outcrop data down Wolf Creek, it becomes clear that there's not enough room for all of the rock units above the Menard horizon. This red line shows the elevation of the Menard, what we believe to be the elevation of the Menard, and there's not enough room for both the pink, green, blue, and orange formations to lie on top of that and still be exposed at the surface. So, a soft sediment deformation hypothesis, like this gravity slumping hypothesis, may be possible if, number 1, a detachment horizon lower than the Menard is considered, like maybe the New Albany or some other shaly horizon, and if the local paleoslope in this area could be found to be at least somewhere around 2 degrees, which would be a significant change from the average paleoslope that we understand in the Illinois Basin is supposed to be around, or has been calculated to be around 0.004. So another model must be proposed. And now I'll present a model here that has a tectonic origin. So looking back at the cross-section of Wolf Creek for reference, we'll zoom out from here and we'll show this cross-section as part of a larger model. And just to get us reoriented, here's the geologic map again. A prime was right here and went through just the east dipping panel of this western domain. And now we're going to look at the cross-section B to B prime, which contains both the west dipping and the east dipping panels of this western structural domain. So here we are with the cross-section B to B prime. It's sort of cut off here, but from west to east. And like I said, we've zoomed out from that previous cross-sectional view, but this image is still to scale. And I did that again for the same reasons, so that the bed dips and the bedding and the fault dips were true, and the unit thicknesses could be portrayed accurately. You'll notice here that the data is right here, and I've carried the faults down to depth, which is just speculation. These are all speculative, but I envision the faults being carried to depth, merging with a vertical fault in the basement. And I propose a fault model where the system of normal faults at the surface is part of a larger tectonic structure called a negative flower structure or a pull-apart basin. And they're called such because they look like a tulip in cross-section, or for those of you who relate better with the ginkgo leaf. And the structures like pull-apart basins and negative flower structures form along strike-slip faults that have a component of extension. And it's this component of extension along that strike-slip fault that allows these blocks to subside. So now, that was a cross-sectional view. We're going to turn to plan view and look down on the area. And here's the tectonic model from that view from above. So in structural geology, we use something called a strain ellipse, which tracks deformation in rocks and fault zones. We start with a circle that gets strained as the fault zone moves, and that circle then turns into an ellipse, and the gray areas, or the gray arrows, show the maximum extension and maximum compression directions. And we see here within this model that the normal faults in the Wolf Creek fault zone are oriented in the are observed in the proper orientation to suggest that the Wolf Creek fault zone underwent nearly west-southwest to east-northeast extension. And remember, the Mississippian units are faulted and overlain by the Pennsylvanian rocks, which suggests that this faulting occurred in late Mississippian to early Pennsylvanian time. And the faults in the Pennsylvanian sediments suggest fault reactivation during the early Pennsylvanian as well. So this tectonic model I propose shows that the St. Genevieve fault zone on the whole underwent an episode of right lateral strike-slip movement, which produced a component of extension in the region between the main St. Genevieve fault zone and the Pomona fault. And a bend in the strike of the main fault zone may produce a pull-apart basin in this geographic location. So to take that one step further, let's think about progressive deformation. So that means movement of the faults through time. What we see is, and if I go too fast through this, maybe we can discuss it at the end, but what we see is that a strain ellipse fitted to each of the structural domains. Here's the eastern domain, and here's the western domain. We can see that a strain ellipse fitted to each of these structural domains suggests that the eastern one had formed first in this orientation, progressive shear rotated it counterclockwise into its present orientation, and then the western domain was formed later and has not rotated from its original position. So now I'll show you a simplified block model to reiterate my point about these negative flower structures. So here's an idealized model by Woodcock and Fisher. The negative, of course, means dropping down in elevation, and the flower part is from the shape of these in cross-section. That's how they derived the name. And so they show this type of structure forming along a bend in a strike-slip fault. They see the initial fault trace here. As you get movement along this fault zone with a right lateral sense, we get extension in the orientation of the dotted arrows, and it causes extensional faults to form in an oblique orientation to the strike of the main fault, or to the strike of the major fault. And the final state shows, we can see a block diagram here, where there's the map view here and the cross-sectional view here, and we see these blocks dropping down and merging with a high-angle fault at depth. So Remember how I showed that the tip of the St. Genevieve Fault Zone occurs near the location of the Wolf Creek Fault Zone earlier? I asked you to keep that in mind. So I propose here that the Wolf Creek Fault Zone is spatially associated with the tip and termination point of the St. Genevieve Fault Zone. I think that the propagation of the St. Genevieve Fault Zone, as it was reactivated throughout geologic time, resulted in fault splays like these ones, and these ones, and these ones. That resulted in fault splays like those, and the Wolf Creek Fault Zone is one of those systems of fault splays. And here, at a much different scale, the scale of 1 foot, we see what's called a horsetail fan at the end of a shear fracture in gneissic rock, so not sedimentary rock, but metamorphic rock. And I think that looks, this geometry of that main fault and these splays coming off it, looks quite a bit like the tip of the St. Genevieve Fault Zone there. And I think this type of model is important to understand because structures like this one may occur along other mid-continent faults. And now I'd just like to talk a little bit about the global tectonics at this Mississippian-Pennsylvanian time boundary. So things were much different during this period of Earth history that the faulting along the St. Genevieve Fault Zone took place. During late Mississippian to early Pennsylvanian time, about 325 million, beginning at about 325 million years ago, South America, Africa, and Europe were colliding with Laurentia, or what we now know as North America, on the east, forming the supercontinent of Pangaea and building the Appalachian Mountains. So at this time, the South Pole was covered by a huge continental ice sheet, not the case today, and California did not yet exist. So just to emphasize, during this time, a vast mountain building event was underway, building the Appalachian Mountains of the East Coast and transmitting tectonic forces thousands of kilometers into the continental interior to places like Illinois and Missouri. And during this time, many of the faults, as shown here by the short black lines, were active during this late Mississippian to early Pennsylvanian orogenic event. And in the Illinois basin, there were several faults that were reactivated. And so we can envision the pre-existing